This is Exploring Creation with Physical Science, 3rd edition, Module 9, Physics, Waves, and Sound. We're in the student notebook. We're going to go through and give you a quick rundown of what's in the student notebook and what we are learning about in this module. What is a mechanical wave? Well, a mechanical wave is a disturbance in matter that transfers energy through the matter. It could be your arm splashing in the water. It could be a mechanical wave maker that's actually legit a machine, but it could be a boat that makes a wave in the water. Mechanical wave doesn't have to be a machine. It's just a disturbance in matter. It doesn't have to be through water, but all of my examples were in water. It could be an airplane making a wave in the sky with the energy, the air molecules all making waves around it. Yes, it could be anything. What is medium? A medium is matter through which a wave travels. Should have touched up my nails before I did this today. Oh well. All right, so so let's give an example of that. A medium. Let's see here. So I hear Maisie sighing over there. Thanks, Maisie. If I talk to you through this device, then that device that you're holding or watching on plays that back to you. That is the medium through which we are communicating, and that those sound waves are being collected and then communicated back through. So, but it could be just simply a vent or a wall. You know how we can talk through a wall. Maybe that wall is the matter through it, is the medium through which our sound waves are traveling. But it doesn't say sound waves, it says waves. It could be any kind of wave, right? So we're going to learn a little bit later about radio waves and other kinds of waves that are we don't see or feel, and that, boy, they go through everything almost, don't they? So, all right, so let's see. Transverse waves. Transverse waves. There's a few types that we're going to look at. And the transverse ones are, I'm just going to show them to you because that's way better than telling you all these fancy highfalutin descriptions, okay? So I think of a big T when I think of transverse because we have the direction of the vibration going one way, and we have the direction of the wave going the other. It's actually kind of traveling this way. You can see it would kind of follow along that, even though it's being shook this way. Okay, so transverse gets vibrated one way, and then the wave travels the other way. So down below we have, I like mine better, even though it's the same thing. You can see it a little better at this angle because the paper's not bent there. But this is a diagram of a wave. And at the top we have the crests. The bottom we have the troughs. Think of the pig trough where they would eat. They wouldn't eat out of the top. They'd eat out of the bottom of a trough, right? Think of surfing on a crest of a wave. The crest would be at the tippy top of a wave. And the amplitude is how high that wave would be from resting position, or in this situation, in my example, how high from sea level maybe the waves are. The amplitude of a surfer's waves might be 8 foot tall. That's a big wave. So wavelength is from any point in a wave from the same point to another one. So assuming they're consistently the same size, you can say the wavelength is from this trough to this trough, or this crest to this crest, or this point right here to this point way over here. Okay, because not here, that's not the same point on a wave. This would be the same point on the wave from here to here, or from here to here. Okay, So that is a wavelength. And there's this cool symbol. It's like a Greek letter for wavelength right there. Isn't that neat? Wavelength. There you go. All right. Longitudinal wave. This is a different kind of wave. We have, I think, 4 kinds of waves we're going to look at. Longitudinal wave is a wave in which the vibration of the medium is parallel to the direction of the wave that the wave travels. So here's an example they have here. I did not label this one. Why did I not label this one? I missed it. Heavens. Well, I like their example here in the book. This is a slinky. And in the slinky, you can see that if you stretch it out and then add energy by pushing or pulling the end of the slinky, you should see something figure. You can kind of see how it, if you take the end and you go boing, 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 you know, like that to the end of it, it makes these waves that go along the same direction that you're pushing on it. And so the direction of your pushing on the slinky makes the waves in the same direction, and those are called longitudinal waves because they're the same direction. There's no T there, right? Parallel means side by side, not touching. All right, so that's what's going on with longitudinal waves. Here is an example of what was my diagram should have had. And this is why I was having trouble understanding what rarefaction was, because I never labeled this. My goodness. All right, so let's read it here. The sections where the coils are closest together, notice those, and those are called compressions. All right, so where's compressions? Right, yeah, there's the compression. There we go. Here's another one, doop, boop. Right, now, let's see here. Where the coils are pulled farther apart, it's called rarefactions. So rarefactions are these points here where it's pulled further apart. They're more taut, or they're not taut. They're less taut. They're more expanded between them. Okay, and so if these are the waves. This is a wavelength from here to here, but I would venture to say from here to here could be counted a wavelength as well. If you can go from the same point on a wave to the same point on another wave, that's one wavelength. Source direction, I think we covered it all. So compressions, rarefactions, wavelengths. Boom. Moving on. Surface waves. All right, so I made a fancy picture over here, so we're going to come back on over. A surface wave is a wave that travels along the surface of a medium, usually like water. It's a combination of both transverse and longitudinal waves. Just imagine a bottle floating on top of water. Oh, it almost looked like it was moving there for a second, didn't it? I'm going to shake it. There we go. There, it's just floating in the water. So there's a circle around it to show that it's kind of ends up, because of the the transverse waves, the longitudinal waves acting on it at the same time, because of the random waves going on around it, they ends up kind of going into in a circle position, circle like motion, and it doesn't end up moving. It doesn't actually go anywhere. A current might change that, but if you ever notice, if there's no current, like how a wave doesn't necessarily move you if you're sitting on a donut type of blow up water floaty toy, if you're you don't necessarily move unless you actually paddle yourself, try to force yourself to go somewhere and give it some momentum. So if the direction of the wave is going this way, doesn't mean this goes anywhere. The water molecules don't go anywhere. The bottle doesn't go anywhere. They all kind of just do this little circle because of the transverse and longitudinal waves that are kind of just causing a little circle to happen there. All right. What is an important point about waves? Well, according to the text, an important point is that they carry energy through a medium without transferring matter. So I already said that. And on our own. how are they formed? A source of energy causes a vibration to travel through something, like splashing or jumping into the pool. On my own. All right. We have a little diagram here. Transverse waves, perpendicular. They go opposite directions. Shaking as a rope side to side. It says a slinky bit. Longitudinal, like I ventured an accordion might be another way, but it would be easier to make actual waves with a slinky, and so that's maybe not the best example. Surface waves, both perpendicular and parallel, and ocean waves are a good example of that. I said 4. What was the 4th one? I thought we had a 4th one. No? Okay, sorry. I wish I was wrong. All right, so let's see here. We're on page 261 now. How high or low are waves? That's called amplitude. So you want to go surfing on a high amplitude day, and you want to go boating on a low amplitude day. I'm pretending like this is all water all the time, but these waves apply to radio waves and light waves and all sorts of different kinds of waves, any kind of wave you can imagine. So there's amplitude. It's just so much easier sometimes, to think about things in terms of concreteness. That's probably why God sent Jesus, right? So we can have something to see and understand God by. And so here we are. I'm trying to talk about water again, but more energy a wave has, the greater the amplitude. So what this was saying was that if your brother gets in the pool and makes a big what's it called? Bomb. What's it called? It's a bomb. I'm losing my words. Not a belly flap, when they just basically curl into a ball and jump into the water. What's that called? I forget the word. And they come into the water like that, and they splash you really big. Well, the more energy they put into that, the greater the wave that hits you, right? You get a really big wave all over you. But if they just kind of like boop, slip in the water, maybe you don't get so much of a splash on you. So the more energy a wave has, the energy can increase the amplitude of a wave. And that's not just for water. Don't ask me what this grossness is here. We've had this around. I've been trying to get this work done and this video out to you for a couple of weeks. So the goodness knows all grossness. Life has happened on this book. All right. So probably food of some sort. All right. So let's see here. We've got lots of little details here. We have frequency and period here. So the number of complete cycles in a given time is like 1 cycle per second. Okay, so we can see if this is time, 1 second has passed, 1 cycle, one wave has happened. That's called 1 hertz. If 2 cycles happens in a second, well, that's 2 hertz. By George. And the period can change from 1 second to half a second. And so let's see here. Let me get this right. The period is how long, this is what's confusing here. It's not just how long they choose to make these little things here. How long does it take for 1 wavelength to happen? And in this situation, it's a half a second because 2 are happening in 1 second. So the period for this would just be 1 second because there's only 1 wave happening per second. So 2 aspects of this. The hertz focuses on the cycles happening in the seconds, and the period is referring to the amount of cycles in a second. Okay, so well, how can I say that? How many cycles? How much time does it take to get 1 cycle? That's what it's referring to. So so we've got a half a second here because we got in 1 second 2 cycles. So it's just a little bit funny the way to say that there. So frequency and period and frequency and period and wavelength are inversely proportionate to each other. So the more wavelengths we have, the lower the frequency and period. The higher the frequency and period, the lower the wavelengths. So it's inversely proportionate. That's what that means. And this is a math concept you need to learn. That is just a really quickie diagram of an inverse graph right there. And I think I've got another one, a directly proportionate one. When it's directly proportionate, it goes this way out of the axis there. So we have x, y, 0, and so high, low. All right, and over time. All right, one is going. Anyways, okay, rambling here. All right, wavelength. The distance between a point on one cycle of a wave and the same point on the next cycle. We already talked about that. So if it's got a long wavelength, you know what that is. Short wavelength, boop, boop. These are tiny little guys. It doesn't matter where they are. I added some little arrows there so you could see anywhere from same place to on one wave to the same place in the next. That's a wavelength, short or long. All right, wave speed. All right, this is a proper equation, people. We need to know what this is. Speed equals wavelength, like that little guy, times frequency. Okay, now don't forget, we scientists like to interchange speed and velocity, even though one of them has trajectory. And so we can say V equals lambda or wavelength times frequency. Okay, it's a lambda, a Greek lambda. That's what that little guy is. Isn't it weird? I like it. I'm pointing wrong right there. It's hard to actually do this. I obviously am not the best camera person in the world. I'm apologizing here. All right, so we're at example 9.1. Someone shakes a jump rope. Why would they shake this jump rope? I don't know. Wavelength is 1.2 meters. Frequency, 3.3 hertz, or 3.3 let's remember what we were talking about. It's 1 cycle per second. Okay, this is 1 cycle per second. And velocity is, we have no idea. That's what we're trying to figure out. There's how we're going to figure it out. And here's us plugging in all the numbers. I'm going to make it so you can see all of how I did that. Okay, so we can plug in our, we've got wavelength up there, 1.2, boop. And we've got frequency, 3.3, boop. All right, and then we have, you know how you can put that over 1. And then I wrote this out for you guys so you can see. We would put the meters over 1 and the 1 cycle per second here. Cross out the ones. Zoop, zoop. You got meters per second. 3.96 meters per second. That's how you do that. Okay. You can put anything over 1. Just hold. All right. What is the frequency of a wave? So we've got this situation. Our wavelength is 0.5 meter. Frequency is, I don't know, in hertz. Velocity is 3 meters per second. Let's see what we're going to do. So we've got this. We want to reconfigure this so that we can determine frequency. So if we have multiplication here, we need to divide both sides, right, in order to get f alone. So we're going to divide this side by lambda, and we're going to divide this side by lambda, and there we go. Velocity times, or divided by lambda, equals frequency. That's how we got that. It's not magic, people. All right, so we've got frequency equals, let's put it up, plug it in. Velocity was 3.0 over our lambda, which is our wavelength, which is 0.5 meter. And we work it out. We got 6.0. Now look how we switched it over from meters per second or meter to 1 cycle per second, which is the same as a hertz. Whoop woo! We made hertz. Yay. And it didn't even hurt. Ha! All right. 9.4. Longitudinal wave is suddenly stretched so that its wavelength is increased. So remember, longitudinal, side by side, they were parallel waves. If the speed of the wave does not change, what will happen to this wave's frequency? Well, since wavelength and frequency are inversely proportionate, frequency is decreased. All right. You know what? I missed one. That was 9.4. Down here we have 9.3. How does the amplitude of a wave relate to a wave's energy? Well, remember we talked about that. The bigger the bomber in the in the pool, the bigger the wave. So this is the size of the giant splasher gets in, jumps into the pool, the bigger the wave. They go up together. So that was directly proportionate. This one is inversely proportionate. It is the opposite. One increases, the other one decreases. All right, we're going to skip the last one because all the answers are in there. And I'm going to move on to page 267. Explain how you hear using this figure below. Isn't this fascinating? I think it's fascinating. Right, here we go. We've got sound or vibrations happening right here. And we've got the eardrum, also known as the tympanic membrane, right there. Isn't it weird? Looks like a contact lens or something. And then that vibrates from those sound waves hitting it, and it hits those, sends signals and vibrations to the ossicles, and that in turn sends a message to the cochlea that converts those vibrations to electrical signals. Those electrical signals then are sent to our brain through the auditory nerve. Right? Yeah. It goes into your brain. Up, like that. Right? So that's what's happening there. So don't forget those words. We've got eardrum or tympanic nerve, or tympanic membrane, ossicles, cochlea, into electric signals. The cochlea does that. And then it goes up into the brain through the auditory nerve. Woohoo! All right. So what we got next? So we are going to complete the problem solving. Looks like, oh man, I had ambitions to do all these cool things with you guys and do these feeling sound waves. This would be the world's longest video if I did that. So we're going to keep it short for you. You're welcome. Complete this problem solving steps for this one. All right. So if the temperature is 68 degrees Fahrenheit or 20 degrees Celsius, same thing, what is the speed of sound? Well, they want the temp in Celsius. What is the velocity in meters per second? Let's look at our equation. We've got, see here. This must be, so this one, as I recall, is really cool. I'm going to try to find it here. Example 9.2. It is neat because I like it when there's actual data in our equations, because I feel like somebody else has done a ton of work for me. And here I am just taking their work and making it work for me. And so we've got the speed of sound given by this equation. I'm going to bring you over here. Ooh. This is the equation 9.2 for the speed of sound. Isn't that cool? So V stands for the speed of sound. T is the temperature. And in order for this equation to work, temperature must be in Celsius. So that's important. And that's where we get this information that you're looking at in my book. So let's come back over to it. So there we have our 331 and a half plus, so we got the 0.6 all from them, T meters per second. So the t is the only missing variable right there besides our velocity, right? Speed of sound. So really, there's only one little thing to plug in. That's why we only have one variable up here, because it's the only one we need. How about that? Okay, so let's plug it in. No units listed because it's already in Celsius. So because this T is always has to be in Celsius, you don't have to put degrees Celsius here. That's what they're saying. It's just given that's in Celsius. That's built into the equation. It works as long as it's in Celsius. So 20 was our degrees of Celsius. We're working that out. So those times each other was 12. These plus each other is this right here, meters per second. You can hear my family out there in the hallway talking about dinner. I smell dinner. It smells really, really good. My husband was cooking sausages, I believe. And all right, so let's see here. You see lightning, and then you hear thunder 2 seconds later. If the temperature is, did you guys know this is like affected? The whole like sound, like the speed of sound is affected by temperature. I think that's fascinating. So temperature is 15 degrees Celsius. How far were you from the lightning? See, when I was a kid, we just count 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 after we saw the lightning, and we'd say it's that many miles away. It was 7 seconds, it was 7 miles away. Well, this is much more accurate. So we see lightning, and we're going to assume it is immediate when we, like, you know, even though that's not true. I mean, we're going to start the time based on when we first saw the lightning, okay? A lot more goes into that, the response time and stuff like that. Just even starting a timer, which probably nobody was doing, but that's okay. We're going to give them the benefit of the doubt. Okay, velocity. Boom, boom, boom. We need our T, right? All right, so the T was 15 degrees. Look how I messed that up so beautifully. Don't get messed up, Mrs. Wigton. All right, it's 15 degrees right there. And we work that out to 9, add it together, and we have 340 meters per second. That is how far we were from, no. That's how fast it was going. Sorry. That's, remember, V. We were solving for V, velocity. Now we need to determine distance. Now velocity equals distance over time, but we want to solve for D. We've got velocity, we've got time. So let's figure it out. How did we get to there? Anybody? If we have division over here, we need to multiply both sides by the variable we want, which is D. So we have VT over here and multiplied it by each other, and we got D alone. Yay! So here we go. We're going to take that 340.5 for our V, and we're going to take the 2 seconds that they were so dutiful about noticing it was only 2 seconds, and boom, that's how far it was. This 681 meters away. Well, I wanted to know how many feet away that was, because I don't think in meters. Do you? I don't know. Maybe you're in another country, in England or Canada, and you do think in meters, and that's fine, but I don't. I think in feet. So if it's in feet, we've got meters times 3.281 equals the number of feet. So here's our meters. See? We multiply it out, and it's 2,234 feet. Well, that's awfully far. But we don't know, like, compared to, say, how's that, a mile? No, it's not even half a mile, but it's 0.4 of a mile. Or this is the fraction of it. There you go. Did not reduce that. Sorry. So not quite half a mile away. That's pretty close for lightning, if you're worried about, you know, getting hit and stuff. All right. We're going to move on over here. We're on page 271 now. What is the speed of sound and air when the temperature is 28 degrees Celsius? Okay, we've got T equals 28. V, don't know. Plugging in our T, 28. Boomity boom. And there we go. Speed of sound in air when it's 28 degrees Celsius is 348.3 meters per second. That's pretty speedy. Right. During a thunderstorm, the temperature is 18 degrees Celsius. If you see a lightning flash and hear a thunder 1.5 seconds later, how far away did the lightning actually strike? Well, we've got all of our variables we do know. I believe this is temperature and time, so don't get your T's mixed up here. And we're trying to figure out speed and distance, okay? So plugging in our temperature. Get mixed up here. Temperature, 18. And it works out to be 342.3 meters per second. Now we're going to do that magic again here with distance and move things around. And we multiply those two together, and we have 513.45 meters away. That's how far away the lightning actually did strike. Yep. All right. Moving on to page 273. What does the first paragraph of this section say is important to realize? It says that sound can travel through any substance in which it can oscillate in order to make waves. All right, I found this one diagram in here super helpful. It's on page 329 in Module 9 in the textbook. And it says that the speed of sound in certain mediums. Check this out. Dry air, which is typically how we, maybe not 0 Celsius, but that's cold. This is about average temperature here, right? In the 70s or 80s. We've got the speed that sound can travel in our normal air that we're normally talking at is 346 meters per second. Okay? And is it faster or slower when it's cold? I'm thinking it's slower, right? Yes, because as we go down, it gets faster. All right, so in liquids, it gets faster and faster and faster. We got alcohol, fresh water, salt water, different temperatures of salt water. I guess the warmer it gets, the faster it goes, just like the faster we got in the air. Isn't it funny that the thing that we communicate in the most, which is talking through dry air, is like more slow than all these other things. These are faster ways to hear than anything we actually do on a daily basis. All right, so wood, check it out. Way faster to transfer sound waves. Oh my goodness. Steel, even faster. Aluminum, faster yet. Iron and glass at the very fascinating. So what we want to recognize is why. I was like, why on earth would glass be faster than, say, something really solid like iron or steel? Those seem like even more solid. If this isn't it getting more solid? Actually, no, it's getting less dense. And those less dense sounds allow the sound to travel faster, but there's a limit to how lack of density we can have, how much lack of density, because if it gets too softy wafty, we like, paper towels or, cloth or something like that, it will just absorb sound. So it needs to have the spaciousness between the cells or the atoms in it for it to reverberate, but also have that it's solid enough to bounce off of it. If it's too squishy, it absorbs it. So we don't want to use. That's why a toilet paper roll is not ideal for transferring sound. All right, let's get back to it. I'm back to the page 274 in the student notebook. We're going to go back and forth though because of some cool pictures in this section. All right, supersonic speed. Any speed is faster than the speed of sound in the medium of interest. All right, so if you go faster than the speed of sound, boom, supersonic speed. Those are also known as Mach 1 and Mach 2. So as soon as you hit speed of sound and you start going faster than that, you're Mach 1, twice the speed of sound, Mach 2. So, and I think the highest anybody's ever gone is a little over Mach 3. And yes, you can have like 2.39. So Mach 1.78. So there's degrees of that. All right, what is a sonic boom? Oh my goodness, you know, when your science book says boom like this, it's going to be awesome. And you guys, this is not even oh my goodness, this is so amazing. When an object travels through air faster than the speed of sound in air, Mach 1 or above, travel creates a giant boom. There's a picture of the boom over here, and it's going to blow your mind. Look at this. It is in focus, believe it or not. That is in focus. Okay, that is a sonic boom, you guys. All right, so what's happening is that as this plane is traveling, these waves, they make a wake of just like a boat would in the water around it, only of pressure waves, okay, as it's traveling. So it's making these waves as it just goes along the air. And when the jet speeds up to Mach 1, the wave compressions in front, they're tighter, they're closer together because of the direction. And it's going that direction. So they're further apart behind, and they're closer together in front. And when it catches up to that speed of sound, they all pile up and make boom. Isn't that crazy? That's what's happening. It's wild. It can actually hurt your ears, like damage, destroy eardrums. So no bueno. They actually have a rule that they don't do this. They don't go to Mach 1 or above when get to it, so that they make this sonic boom over residential areas and stuff for these people. And so you might hear some cool fighter jets or some sort of military planes someday going over your head, but they already had theirs. The actual sonic boom, which you are going to experience, is a really cool delay in hearing them. They're going to go overhead, go zoom, you'll see them, and then whoo, you'll hear the big, their sound. That is not the sonic boom. That is simply their sound waves hitting your ears slower than you saw them pass. They were going faster than the speed of sound. Isn't that just the coolest? Oh my goodness. Here's another picture. It's really cool. So this one shows the shock waves. And so, oops, I'm not right on it. Sorry. That's a T-38C. My husband likes to look out the window or outside anytime he hears anything, and he's really good at identifying whatever the plane is, which is super impressive. He can actually usually do it based on the sound of them. That is his job. He's in aviation, so he should be the one telling you about this, not me, because he actually did teach me, so I could teach you. All right, so I believe we are almost done. Let's see here. So we've got decibels. What are decibels? We're going to stay over here in the textbook now. Decibels, they have here threshold of hearing. Let's see here. 0. Whisper is 15 to 20 decibels. Normal conversation, 40 to 50 decibels. Busy traffic, louder. Jet plane takeoff, 120 to 160. Possible damage to ears, 130 is potential there. Your ears, I read in here, it's not, the louder it is, the more likely you are to have your hearing damage. Once it gets past a certain point, you have the potential to have damage to your ears, but your it's not a directly proportionate graph on that one, because our relationship, because your hearing, it works in a way to protect your ears. So it gets too loud and it will offset it. So it'll figure out how to reduce the intensity in your own hearing. Pretty cool, huh? So decibels is how we measure sound intensity, and it is 1/10 of the unit bell. So obviously the deci means 10, and bell is it was named after Alexander Graham Bell. How cool is that? Does this look like I'm just kind of winging it? Because I am a little bit. I didn't get to the thing for this one. I'm sorry, but I did go over this with my son. And so this is the science experiment that we did in class. And let's see here. I need to get to the really cool stuff in the back here. All right, pitch. So I'm on page 336 now in the textbook. Pitch is how high or low. How high? You think I've got a great range, right? No, I'm not Mariah Carey here. I actually have a very limited but low range, actually. So pitch is how high or low a sound is, okay? So sound waves with low pitch have low frequency. Sound waves with high pitch have high frequency. So when you see those diagrams with the waves, if they're really close together, and that's a high frequency, that would be a higher pitched sound if it was a sound wave. If they're farther apart, they have a longer wavelength perhaps and lower frequency, they're probably a lower sound. And in music, we want to talk about, look some pictures we've got going on here. Which side do you think is going to make the high sounds? Which side is going to make the low sound? I think you know. So it's not because it's higher up, it's because it's shorter and smaller that these will make the smaller sounds, okay? Or the higher pitched sounds and have the higher frequency. And the bigger the instrument, I have written on myself, that is not a birthmark. I don't even know what that is. The bigger the instrument, the lower the note. My son just took up a upright bass, and the notes are only low on that upright bass. It's so beautiful to hear all the low notes it plays. It's like in a flute. A flute can play some pretty low notes, but a piccolo cannot play those low notes. A piccolo is a short version of a flute in its own instrument in its own right, and it plays all the highest high notes, and it can play higher notes than a flute. And guitar strings. So if you push down closer up and make the string shorter, you're going to get higher notes. If you bring it, you push the frets down way back here, you're going to have lower notes. Ooh, like that. Ooh. Okay. All right. Let's see. Oh, this is okay. So we've got three kinds of waves, okay? We've got sonic waves. I'm going to just look at the text here. We got sonic waves, and those are the ones you can hear, okay? And they are longitudinal waves. And if they are lower, they're waves that we can't hear. That's what you need to know. And if the wave is lower than we can hear, then so those would be some really long wavelengths and low frequencies. They would be called ultrasonic waves. Low, okay? Lower than we can hear. What does that? Oh, say whales, maybe? Let's see here. You could probably hear that, like some earth movement for like when we have tectonic plates and all the words are gone. I'm just a mom. Okay, let's see here. Earthquakes. They make noise. They're lower noises that are lower than we can hear. Ultrasonic, okay? All right. Infrasonic are the high waves. Oh shoot. Did I say that wrong? Higher. I did. Oh my goodness, you guys. I read it and I'm just going from memory. Ultrasonic is the super fast higher waves. My apologies. Higher than 20,000 hertz. So ultrasonic are the fast ones that are high. Okay. And then the low ones are infrasonic. Okay. So my apologies. Please don't get those mixed up. So infra, think of infrared. And we have, they're going to make that red down low, okay, because we've got the infra is low, the ultra is high. My apologies. So bats can hear sounds that are up to 100,000 hertz, and cats can hear sounds that are up to 40,000 hertz. And so they hear the higher. Which one's the higher? Ultrasonic. I'm going to try to make up for my error there. I just wish I could make a video without messing up somehow, but it's never going to happen. Sorry, guys. All right, whales and elephants can hear the infrasonic, the low ones. All right, Doppler effect really fast. We're going to call it good because I'm about out of storage on my phone. So Doppler effect. When you hear these really weird warpy sounds when an ambulance is going by you, that is because you're listening to it go from like woo, 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 and then it passes you, and they're actually further apart, and so they go woo, woo, woo. Well, it changes, right? But it sounds warped and weird because you're actually getting this crazy combination of first sound vibrations that are closer together and then further away as it passes you. So if you're a bee, you would hit it. Those closer ones would hit you first, and then as it passes you, you would hear them further apart. And so it's going to kind of warp in your hearing a little bit. Crazy, huh? So cool. Oh my goodness. A second. Okay, last thing we want to see here is that we can use these sound waves that we can't actually hear, the infrasonic and the ultrasonic. We can use them to measure the distance of things and see maybe things that we can't actually see with our own eyes, like under the Earth's crust. Second. And see here, down here, we have let's see here, the ultrasonic ruler and sonar. So the we can use these to see when an earthquake's coming, and when a baby is coming. Just kidding. Right here, they use ultrasonic waves in a ultrasound machine to help us see a baby before it's born. And so all that happened there is ultrasonic waves. Ultrasonic were the high waves, or the high frequency waves, and they direct them at a person, and a portion of them get transmitted into the person's body, and they continue until they hit another obstruction like the baby, and then those waves are reflected back, and then the computer kind of generates a picture based on those bounce backs, and they can tell where it's the baby is closer and farther away, and generate a picture like that. So isn't that amazing? And how just that's just really just something, isn't it? And so we can see inside of a person that way. And bats can see inside of a dark cave with the same kind of mechanism of bouncing their sound waves off out, and then they bounce and they listen to those echoes, and they can generate a picture in their minds of exactly what the topography of inside of a cave might look like in the night, so they can get where they're at, needing to go. So these are not audible to us and to our ears, but These are waves that are too high. I believe they're the ultrasonic waves that they use. So that is the long and the short of it. And so I hope you've enjoyed listening to some of the Module 9 information. I hope this sums it up for you. We've covered basically all the vocabulary and main concepts, and I hope this is helpful to you. And I haven't had the camera on me as much because every time I turn it around, it messes up, and it's just hard. So, so anyways, I thank you for listening, and I hope you do have a wonderful rest of your year and do great on your test if you have one. Take care. Bye-bye.